Dear participants, welcome to our Malachit School. And today I'm glad to introduce Mikhail Villaden. He has a PhD degree from the Technical University of Munich. He was working as a researcher and senior researcher at the chair of Communication Networks, Department of Electrical and Computer Engineering, Technical University of Munich. During this time, he had been a visiting researcher with the Royal Institute of Technology in Sweden and Aalborg University in Denmark. His academic contribution include works on wireless communication of Internet of Things and cyber physical systems. And now he will tell us about approaches of stochastic optimization and its application to resource allocation in wireless networks. So, and I just remind you that you can ask any questions in our YouTube chat. Mikhail will choose the best question and the author will receive a branded Malachit School t-shirt. So we can start and I will get floor to Mikhail. Mikhail, please.
Good morning, everyone. Thank you, Vasily, for the introduction. Today I'm going to talk about the stochastic optimization. So let's first manage some expectations. So what this talk is going to be is basically sort of a lightweight, brief tutorial on stochastic optimization, which includes the theory behind it, so the Markov decision process, the planning methods, and the learning methods, which is also known as reinforcement learning. And since I'm a communication network engineer, I'm going to give you here also some examples from my work on communication networks. So as far as I understand, the background of everyone is different, but I'll try to basically boil down the examples to the bare minimum, and I do not assume that you have any background in communications, whereas I assume that you have some background in mathematics. So the content of the tutorial is based on a couple of important books on stochastic optimization. So the reinforcement learning by Sutton and the dynamic programming and optimal control by Bert Sekas. And then the examples are based in part on our work with my colleagues at TU Munich. So let's go right in. So first, let's have some motivating example for the stochastic problems. So let's consider a simple wireless network where you have 2 users and a base station. So the users have to transmit some data towards the base station, and we assume that the users are sharing limited transmission resources. Yeah, so it could be time, frequency resources, and so on. So how do they actually share these resources? So the base station has to decide who transmits first and who transmits next, and so on. And it informs the users with a scheduling decision. So it sends a message and says, okay, user 1, now you go. And then user 1 transmits the data. And it sends another message and says, user 2, now you go. And then the user 2 transmits the data. So that's basically scheduling. That's how scheduling works in current systems, like in cellular systems, for instance. So now, so far, so good. Now let's make the situation a bit more complex. Now you don't have any users, but you have sensors. And the sensors are measuring a certain process and transmitting the state of this process. So for instance, the sensors are controlling the position of a certain object, and they would like to keep this position as desired. Yeah, but the process keeps basically, the position keeps deviating. Now what's happening is basically they transmit data towards a remote controller, which are located somewhere in the cloud behind the base station. And this controller is basically controlling the process which sensor is sensing. Now we would like to send the data again. And now the problem gets more interesting because you should decide whom do you schedule first. So which sensor should you let send the data first? Now, an idea here would be, which is quite understandable, is to schedule a sensor with more valuable data first. So for instance, if a deviation from a desired position is larger. So let's look at this graphically. And let's say the red line represents the evolution of a state value of a first sensor. Now what's happening is that when the sensor is not scheduled, the state is growing. So the deviation is growing and the state value is growing. And at some moments, the sensor is scheduled. So let's say assume here it's scheduled at time X and at time Y. And in that case, the next time step, the controller goes into play and it basically compensates the position and when the sensor value is going down, as you can see here. So basically reset to some random number, whatever. So here in this example, we scheduled the sensor 1 in the time X because it had larger value, as we also thought about in the beginning. Now let's take a look at what's happening in the next time step. At the next time step, we will see that the value of a sensor 2, which is a blue line, is actually growing higher than sensor 1. So it means that if we actually knew what's going to happen, so if we had a way to look up, then we should have scheduled sensor 2 instead. And this problem of actually finding an optimal scheduling or finding an optimal resource allocation, considering the evolution of the states of a system, so considering the delayed rewards that it might not be in this moment, but maybe at some moment later you get a higher value. This is basically a stochastic optimization problems I'm going to talk about today. Yeah. The exemplary problems is multifold. So you could basically apply the tools and you can formulate many problems as this delayed reward optimization problems. So for instance, you could, as I said, from communication engineering, you could use the scheduling, you could do power control with that, you could do interference coordination, access coordination, and so on and so on. As a reward or as a value, you could also use different parameters. So it's an optimization problem. So you can put in the objective whatever you desire. For instance, power consumption, the resource efficiency, latency, or like in my example, which I gave just now, is the sensor data. So this is some kind of value of a sensor of a sensor's data. So, but actually the applications go far beyond that, and the communication examples are probably not even the most illustrative ones. I think the most common examples for these problems are in robotics, for instance, if you want to control a robot, and then the input you send to the robot is actually an optimization problem. Autonomous driving, gaming. So I think this is actually the most probably fun example, is that most of the artificial intelligence agents playing games. So like AlphaGo, for instance, I think it's the first agent which beat a human in the game of Go. So all these agents, in some way, they use theory from stochastic optimization and specifically from reinforcement learning, which I will talk about later. Okay, so that was tuple motivation. Now let's start with the theory behind the topic, and basically the whole framework is built upon a notion of Markov decision process. Basically, what the Markov decision process is. Consider a discrete system. So you have discrete time steps. So let's say time t and then time t+1 and so on. And in this discrete system, you have a state space. Yeah. So your system has a certain state, which can belong to a state space, usually assumed finite. And then in this state, you can take an action, which belongs to the action space. So it could be, you could have a choice of actions. And how do you actually choose an action in a given state is modeled as a policy. So this is the most important, it's one of the most important things, is the policy. Basically, it's the rule, how do you decide on an action in a given state. Yeah, and this is actually the thing which we want to find, so the best rule, best policy. And once you take an action, you get the reward. So, and you transition to the next state, so S prime in that case. Yeah. Now, the thing is that this is a stochastic process. So basically, we do not assume that the rewards in next states are deterministic. So that means that if you take a certain action, you have a certain probability to be in another state and to get another reward. And these probabilities basically represent the environment model, so the model of the stochastic system. Yeah, so basically the so in short is the probability of getting into the state S prime and getting a reward R, given that at this moment you are in a state S and you take an action A. Okay. So yeah, well, why is it called a Markov decision process? Well, it's because the process, underlying process, is assumed to have a Markov property. So I hope you know what it is. But basically, it means that so it literally means it is written here in the environment model. Yeah. So the next state, the transitions, they do not depend on the whole history of state, but rather they depend only on the current state. Yeah. So if you are in a state S, then you don't care what was before. You only care about this state, and from this state you can compute the probability of transitioning into state S prime. Okay. So to put it in another way, so you can think about it as a sort of this two entities loop, sort of. So you have an environment, and the environment is basically generating a certain state and reward, which are fed into your agent. So in our case, it's a scheduler. And the scheduler decides based on the action and basically puts an action into the environment. And then the environment is doing something and generating a next state. So basically, it looks somehow like this. So you are in a state S1, you take an action, you get a reward, and you transition to the next state. Then you take another action, then you transition to the next state and you get another reward, and so on and so on. So this whole sort of chain of events, so traversing the Markov decision process, traversing along this graph, is called a trajectory. So basically, it's a sequence of this state, action, reward sequences. Now, what do we want to do with this, actually? So in simple terms, we want to collect as much reward as possible. So we want to get a policy which brings us the most reward. And while using this policy, we actually try to maximize the discounted return. So if we formalize it, so basically an infinite sum of returns starting from this state, following a policy pi. Yeah. And so why is it a discounted return? Well, the first reason is just mathematical tractability, because otherwise the sum would be infinite. But the second thing is also you need to bring in discount factor to balance out the current rewards and future rewards. So the farther away rewards are, the less value they have. Well, because gamma is less than 1. So the closer is gamma to 1, the higher you value future returns, and the closer it is to 0, the less you value future returns, and the more you value current returns. Okay, so that's fine. And so as I said, we want to find the policy. Yeah? So, so we want to find the best policy. Now, to find the best policy, first thing you need to do is to have a way to assess how good a current policy is. And you do that by the means of two functions. One is a state value function, and another one is an action value function. So what is a state value function? Sorry. It's basically a function which defines the expected return from a certain state if you follow a policy pi. So every value function is actually conditioned on a policy. Yeah. So what does it mean? Is basically we have different states, and in in these states, basically in every state, you can assign it a value function. So you can say, okay, how much value does a state S prime, S2 primes, and this should be S3 primes. How much reward can you actually collect? How much discounted reward can you collect from that state? What do you expect to collect from that state? Now, a similar function is the action value function, which is describing the expected return from a given state if you also take an action A. So it's conditioned on the state and the action. Yeah. So basically, what that means is that for every action in a given state, you can assign a state action value function. Now, and obviously, the larger this function, the better it is. So the more is the value of a state, or the more is the value of a state action pair. Yeah. So now, what about the optimality? So we want to find the best function, or the best policy, sorry, and how would we define the optimal policy? Well, turns out that the optimal policy has certain properties, theoretic properties. One of them, the most important probably, is the Bellman's optimality equation. And what it basically says, so as Richard Sutton puts it very well, of course, that the value of a state under an optimal policy has to be equal to the expected return for the best action of that state. Yeah. So basically, you have to follow the best action, and the value then of a state would be equal to this best action's outcome. Yeah. So basically, if you have an optimal policy, then the value function of that state, and from that you can just take the maximum, so the best action, and that will lead you also to the value of optimal policy of the next state. Yeah. So what it actually is, this formula is basically a recursive relationship. Yeah. So you have here the value of a state, and then here on the right you could see the value of a next state S prime. Yeah. And basically it forms. It doesn't matter from which state you start, so it always holds. So it basically forms a system of equations for all the states, so all the value functions of all the states. Yeah. And you can also formulate it, by the way, in terms of the action value function, but for the sake of brevity, I'm only showing here the state value function. So before we actually go into how do you now compute this optimal policy, let's first walk through an example. Yeah, so let's first get back to our sensors and see how do we formulate the problem as a Markov decision process. Okay, so as a reminder, we had two sensors here and the base station and controllers and so on. And so what is a state here? So basically a state would be then a tuple or a vector, whatever, of values of both sensors. Yeah. So basically you define a state because you have a system of two sensors. So you define a state as basically two values of two sensors. Yeah. And an action is a scheduling decision. So the base station schedules a certain sensor. So let's formulate it as basically a binary vector, also a vector of binary decision variables. So the delta 1 is equal to 1 in the case that the sensor is scheduled, and delta 1 equal to 0 if the sensor is not scheduled. Yeah, and then the sum of this decision variables is basically at most 1. Yeah, so you cannot schedule more than one sensor. Let's assume that. And then the reward is basically the sum of states transmitted. So the sum of states of deviations of both sensors, which you could reset by scheduling. So it can be basically expressed in the terms of action and state here. Yeah. Okay. So how would the policy look like here? Yeah. So basically we have two sensors, so they both have different states, and our state is a combination of both. So we can visualize a policy as a lookup table. So you can say, okay, here on the y-axis I have a sensor 1 state, and on the x-axis I have a sensor 2 state. And now basically the orange part represents, this is an example, yeah. Orange part represents where you schedule sensor 1. So if basically sensor 1 state is this large and sensor 2 state is this, then you schedule sensor 1, and similar for sensor 2. Okay, yeah. So that's basically how we would formulate an MDP out of the original problem. And now the question is really, how do you compute an optimal policy? Now, in general, there are two methods to do that. One is called, so there's a lot of different terminology, but let's say according to Sutton, there are planning methods and there are learning methods. Yeah, and you will see a bit later why learning is learning and why planning is planning. So let me explain you a basic principle of a planning methods. So there are many of them. There are two main methods, but there are many variations. So first of all, the assumptions here are, first thing is that we work with a finite Markov decision process. That means that the number of states and number of actions and rewards are finite. Yeah? So we can count them. And the second thing, this is a really important thing, is that you know the model of the environment. So let's maybe jump back quickly to the model of the environment. So you basically know the transition probabilities between all the states and rewards. Yeah. So you have a distribution somewhere. Yeah. So it's expressed in some form. And knowing the model and knowing that the number of states and rewards and actions are finite, what you want to do is basically with planning methods, this is why they're called planning, you pre-compute the optimal policy in an offline manner. So basically before you start the system, knowing the model, you can already compute the optimal policy. How do you do it really is by the principle of iterative computation and dynamic programming. So it's actually, if you're familiar with the concept of dynamic programming, this is exactly the planning methods. Yeah? So which consists basically of two steps. Yeah? One is called usually a prediction step, and the second step is called control. Yeah. And you could basically, you have to alternate between these processes until they converge, because it's a recursive relationship, so it maybe take a while to converge. And the prediction step is when you evaluate or estimate the state value function or the action value function. And the improve step, the second control step, is basically when you improve your policy. So this is, you have to evaluate under a given policy, of course. And then you improve is when you adjust your policy according to the things you've learned. Yeah. And the policy evaluation part, so this is basically relying on the relationship between the state value function and then the next state value function. And the policy improvement step is really using the Bellman optimality equation and basically greedily, so updating with respect to this value function. So it takes the best action at every state. Yeah, that's a greedy update. And you can actually combine this. So you can combine the steps in a different manner because you have to do it multiple times for it to converge. And one way to do it is called policy iteration. This is when you take a policy, a random policy, you do the evaluation step until it converges, and then you update the policy, and then you repeat this process. Yeah, so until you converge to an optimal policy. And the value iteration is another option of it. This is where you do not repeat until convergence for value iteration, but you do one step of value iteration. So you do just one look ahead, and then you directly improve a policy. And when you do another step ahead, and then you improve a policy again. Yeah. So this iterative process, this iterative computation is what's behind it. Okay. This is just a basic principle, so I'm not giving the full theory and so on, but we will also walk through some examples. So this is how you can formulate one example of the value iteration. Basically, for each state, you compute this estimate of the state value function. So independent on the, I mean, it's actually dependent on the policy, but you don't really see it because you don't explicitly consider a policy in the value iteration. So you basically update the estimate according to the Bellman equation, Bellman optimality equation. and then you repeat it for every state. And then you repeat the whole process until it converges. Yeah, so basically until your updates are small enough not to care about. So there is actually a really common example. So if somebody has a view theory in, background in graph theory or in computer networks, there is a shortest path algorithm, which is called Bellman-Ford shortest path, and this algorithm is basically exactly the value iteration. So yeah, I'm going to walk you a bit through some sort of tricks or some special cases which I think are quite important for value iteration. And one of these cases is when you have an infinite MTP. So it's actually quite a lot of problems in real life when you don't have a finite state space. Yeah, so you have to do something with it. And one way to deal with an infinite MTP, this is quite effective, is a state augmentation. Yeah. So let's say this is your states. Yeah, from 1 to m+1, and what you do then is, okay, you say states 1 till m, I care about them, and the state m+1 and whatever is later, I don't care about them. So then you can just model it as you change your model to assume that the transition probability into this state is 0. Yeah. So this is approximation, but actually this could be a really valuable tool. So the thing is that in your problem space, in a state space, it's often the case that there are states which will never occur in real life, or if they occur, you don't care about it. So for instance, the agents playing the Go, or backgammon, so all these artificial intelligence gamers, let's say, they tend to do really badly in some weird situations which actually never occur in the games with professionals. Yeah. So they will beat professionals, but then if you make up a situation which professionals would never bring you to, they would make really bad decisions on that. And it's because they don't actually consider the states, because they do some kind of state augmentation. Second thing is, so this is a really common thing in the control problems, so in robotics and so on, is when you deal with continuous space. Yeah. So let's say if you control a robot, or if you control a car, actually the car is moving and it doesn't move in steps. Yeah. So there is no explicit discretization there. And how do you really deal with it? Because you cannot go through all the continuous state, because again, this is an infinite space. Now, when you usually apply discretization, so you just say, okay, my state space can be split into smaller chunks, and I just consider each smaller chunk as one state. So the other thing is that these parameters, they play a big role in your performance. Yeah. So you have to somehow adjust them to your case and see what works for you. So to exemplify this, on the right is basically a graph showing the result of such value iteration and how does it perform on a scheduling problem. Yeah. So you don't have to go into details of a scheduling problem, but basically what we have on the x-axis is different discount factors, and on the y-axis is a negative of total value. What does it mean is basically, well, we had a minimization problem, so we wanted to minimize this. So the less, the better. Yeah? And different graphs correspond here to a different number of states considered before augmentation. Yeah. So the higher is the M, the more states we consider. And what we see here is that, well, you have to really search for this space. Yeah. So if you consider only like 15 states here and disregard the remainder, then the performance is really uneven and quite bad. And the more states you consider, of course, the better your performance gets. But then at some moment it hits diminishing returns. Yeah. So let's say the performance of M17 and M25 and M20, they are really close together. Yeah. So you have to like do the search for these parameters and then see whatever works for you. And similar is for discount factor. So in that case, considering the future, so weighting the future higher was proven to be better, but it can be different for your problem. Yeah. Okay, so a little more of just caveats or like potential issues with planning methods. So the first thing is, of course, I mean, you saw it. Yeah, we search through the whole state space, and that's a lot of states sometimes. Yeah, so this is a curse of dimensionality. Yeah, so the planning methods themselves, they're quite computationally efficient because they are polynomial in a number of states. Yeah, so it's not an exponential graph. But what is an exponential graph very often is the number of state variables and its relation to the number of states. So if you increase the number of state variables, then the number of states grows exponentially. So consider the number of sensors, for instance. Yeah. So we had a policy. So before that, this is a two-dimensional thing, yeah, because we had two sensors. So the lookup table is only two-dimensional. Now, if you add a third sensor, it's not like you're adding a third dimension. So you're actually basically adding a third dimension. So your lookup table is basically mirrored also along the third sensor axis. Yeah. And then if you add a fourth sensor, then you get a fourth dimension and so on and so on. And it's easy to see how it's growing exponentially. Next thing is, so how do you actually control this scalability? Yeah? So how do you make sure that it doesn't grow to be infeasible, the problem, yeah? So that you can still compute it. So one thing is, as I mentioned before, you could play with discretization steps and state augmentation. So the more state you augment, the less state you consider. This is fine. And you can also, like if you discretize a continuous space, then you can just discretize into larger chunks if it works for you. Yeah. And the third thing, which is sort of a generalized idea of discretization, is the state aggregation. So it's just that you might not want to distinguish between some states, so you consider them as one state. Yeah, and this is called state aggregation. So there are also other ways to speed this up. So to make it, let's say, more practical, as one is a synchronous value iteration, for instance. This is basically, so in normal value iteration, you just go through all the states one step at a time. Yeah, and these computations might take longer, so you have to wait for all, you cannot parallelize it. So you have to compute all the states and then move on. And in asynchronous value iteration, you basically do not wait for all the steps to update, but you just update them in whatever order it comes. Yeah, and it makes things a lot faster. Now, finally, there are two more things which are really critical when you use planning methods. One is some Markov decision processes are actually not observable. What that means is that when you have an agent, you don't actually see the next state. Yeah? You might see only the reward, or you might see only part of the state. So for instance, you might see only the sensor 1 state, but you don't know what's happening with sensor 2. Yeah? And you only observe the reward. The second thing is that the planning methods, as I said, they rely on computation. And this computation is impossible if you don't have a model of an environment. Yeah? So, and it's very often the case that it's either too complex or it's just not available, the model. Yeah. So for instance, again, autonomous driving. Yeah. So maybe you can compute the probability of a car moving forward, but you cannot compute the probability of a pedestrian jumping on the road. Yeah. So this is something you have to learn by experience. And this brings me basically to the next part. Apart from planning methods, you have also learning methods, which do not rely on a model and which are also coping much better with partially observable Markov decision processes. Okay, so, and by the way, the learning methods are also sometimes referred to as reinforcement learning, but actually the whole topic of stochastic optimization is often referred to as reinforcement learning. So what's the basic idea behind learning methods? So the first premise, as I said, is environment model is unknown, or it's assumed to be unknown. So what does it mean? You have a state S, and basically from that state, you take an action A, and before you take this action actually and observe what's happening, you have no idea what's happening. So you don't know the probability of getting a reward R, a probability of getting into state S prime, and so on. So as you can see, this already breaks the rule for planning methods. So what do you do? And well, you learn the model, yeah. or you learn the solution. So basically, the idea is that you interact with the environment in order to estimate your state value function or action value function. And because you interact with the environment, you basically do not actually work with a state value function or action value functions, but rather you work with their estimates. So the cycle then is basically the same as what you've seen before. But in this case, you have to observe the reward and observe the state, and then update your estimate, and then you repeat the whole process. So there are really a lot of methods, learning methods, way more than there are planning methods. And the most popular one, probably everybody heard about it, and probably many of you know, is quite simple, is called Q-learning. So the name comes from, first of all, it should give you already a hint that we are not working with a state value function, but rather with an action value function. So what we want to do is basically we want to estimate the optimal action value function by using this sort of called Q table. Yeah. And what is a Q table? Well, it's a table. So basically, it's really a lookup table for every state and for every action. You have a certain value, which is exactly the Q function estimate. And what you do then is basically you take an action, you observe a reward and the next state, as I said before, and then you update your Q table estimate. And then you repeat this process. So how do you do the Q table update? Well, basically, you use your current value, and you use a certain parameter which is called basically a temporal difference error. So what it is, so you can see from this formula, so from the highlighted part, R plus gamma max over A, QS prime A. And this is basically the new value which you have just learned. So this is what you just observed. And on the right-hand side, you see the previous value. So what it is basically it's a difference, yeah. And then you apply a certain learning rate, and you hope for your Q value estimate to converge. So it's sort of the gradient descent you're doing here, yeah. So you basically, this is a gradient, yeah, and then you're just updating your estimate with the gradient. The difference here, so the key point really, the difference to the planning methods is that in planning methods, you had the chance to compute the expected update. And here you don't have it because you don't have a model. So you do a sample update. So you obtain a sample by interacting with the environment, and you obtain this state reward sample, and then you do this update. Yeah. So another thing to notice here is that, as I said in the planning methods, there are two steps. There is an evaluation step and improvement step. Yeah, so you try to evaluate the policy and you try to improve it. So here they're combined together. Yeah. So the maximization here over actions should remind you of the Bellman optimality equation, and it's basically the improvement step. So this is where you take the best action. And the evaluation is basically that you update your estimate all the time. So they are combined in a single formula. Oh, that's nice. So what do you do with this Q table? Well, at some moment you converge to the value which you are happy with, and then you just use this Q table greedily as a lookup for a best action. So you are in a state S, and you just take the row corresponding to the state S, and then you just pick up the best action in this table, and then you're happy. Take this action. So let's walk through an example, and this example will be a bit more involved than the previous one. So now we do not consider a scheduling problem, but rather a random access problem. It's a well-known problem in medium access control literature. So assume you have a base station and you have a lot of sensors this time. Yeah. So you have so many sensors that you actually do not know how many of them want to send the data at a given time. So the consequence of this is that you cannot schedule them directly. You cannot say, user one, now you transmit, user 2, now you transmit, and so on. You cannot do it because you don't know who is active. So what you do instead is you send a probability, you broadcast a probability for every sensor to use to decide if you want to access the medium, so if you want to send data or not. So here, every sensor, so they broadcast a probability, and every sensor draws a random number and compares it to this probability and decides probabilistically to send the data or not. Now, what happens if multiple of them send in the same at the same time in the same resource? Well, a collision is occurring. Yeah, a collision is bad. So none of this data is received, and we are not happy. Now, next time you update your access probability, you send it again, and then they draw a random decision again. And let's say this time only one user transmits in the resource. This is good. So it's success. The data is transmitted, the data is received, there is no interference. Then the third case here is, let's say you send a probability and it was very low, so nobody transmitted. This is an idle resource, so you waste your resources, you waste your time, and that's also bad. Yeah. So what we want to do in such situation is we want to choose the access probability in a way to maximize the number of successful outcomes. Yeah. Okay, that's a problem. And how do we actually formulate it in our optimization framework? So let's define a state as the observed number of successful outcomes. So you have multiple resources. So you can have multiple collisions per time, or you can have also multiple successes, or you can have some successes, some collisions. And this is exactly what you use as a state. So you record a number of successful states, number of idle states, a number of collided states, resources. Sorry, not states. And the important thing to notice here, so when I said before that some processes are not fully observable, and this is exactly that case, because your state is actually the number of active users, but you have no idea of knowing it as at the base station. So instead, we use this sort of observation as our state approximation. So it's not a true state. As a reward, we use the number of successes, so the number of successful resources. And as an action, we have the access probability. Yeah. So the probability you broadcast, and you want to find the best action, so the best policy. So depending on the observed states, you want to find the best access probability. Okay, so what do we get actually by applying Q-learning to this framework? So here you can see one of the examples from one of the papers. And basically on the x-axis, you have a number of successful outcomes. On the y-axis, you have a timeline. Yeah? And the upper two lines, so the ones which go sort of direct, they represent the best case. So basically, these are two policies which are almost ideal. So you assume that you know the number of active users and you just choose the best access probability for this number of users. So this is a best case policies. There are two different policies, but for the sake of this presentation, let's not distinguish between them. And what you see in the lower parts of these three policies, which sort of go up, they are the policies we learned using Q-learning. And the outcome here is, so if you check like the right-hand side, so later in time, the policies are actually performing pretty good. Yeah, so they go really close to the best case without actually knowing the real state. The things to note here, so you saw here like 3 different learned policies, yeah, and you see that they converge to a certain point, and this point is not always the same. So basically what they differ in is in the exploration phase, yeah. There is a trade-off between exploration and exploitation in Q-learning, because you want to update the Q table for every state action imaginable, and you want them to converge. And to update all of them, you need to go through all of them. So it takes time, and while doing this, you actually do bad decisions. Yeah, so you choose the actions to update the Q table, but you actually do not know the best action. Yeah. And this is why in Q-learning is common to, or in general in learning methods, it's common to distinguish between the learning phase and the performance phase. So in the learning phase, you do whatever you want to get this experience done, yeah? So to learn this Q function. And in the performance phase, you use this knowledge to actually get the results. And of course, the longer you learn, the more resources you waste, but also the better policy you could learn, because the better estimate you can obtain. And there is a whole science behind how to do that, really, and how to switch between the phases. And this is really a heuristic approach. It depends on the problem, depends on many things. The easiest way to do it is, I think this is what we've done here, if I remember correctly, then this is basically, you can adjust the learning rate at some moment for a gradual transition. Yeah. So here you could see that the baseline learning rate was producing mediocre results. And then at some moment we decide, okay, enough learning. So here the learning phase was only, so it's 10 to the 4 frames, yeah. And here was 5 to the 4, and here it was 8 times 10 to the 4. Yeah. So the longer learning phase you get, the better results eventually you get, but the longer is your learning. So what are the ways to really speed up the exploration? And they're really important, actually. You can get really better results with using some speed up. So one way is to to use a guided exploration. So as I said before, talking about value iteration, there might be some states which you do not care about. Yeah, so these are the states which maybe never happen, or the ones where you anyways don't get much reward, or anyways, ones you do not want to consider. And you can use this sort of as a guided exploration. Yeah, so you can guide your exploration and you just don't want to explore, or you explore less some states. Usually you do a state exploration by the means of some random distribution from which you draw the actions. Yeah, so you can have, so here in that case, in the learning phase, we used a uniformly random sampling. So we choose any action randomly at any time. The other thing is that if you have a policy, if you have some kind of policy, it might be not the best one, but you want to improve it, then a good idea usually is not to use the full spectrum for exploration, but only to use the things which actually happen when you follow that policy. So you basically record the distribution of actions at every state according to that policy, and then you just sample the actions from this this distribution. Yeah? So this is called trajectory sampling, and it's shown to perform pretty well depending on the initial policy. And there are many more ways. Yeah? So this is this is really a whole science in itself. Okay, so that's to the Q-learning. Yeah? So what we saw here is that it can achieve really good results without even knowing the state. So it's a partially observable MDP, and it kind of converges relatively fast. So here we are talking, so 10 to the 4 frames is 10 seconds. So basically after, let's say, 80 seconds, we have a really good convergence. Yeah. Okay, so what else can we do with learning methods? Yeah? So what are other things which we can consider? So what you usually want to do is, as I said, you want to really do exploration quick. You want to train your agent or train your optimization mechanism faster. Yeah? So one way to do it, which is really advocated by Sutton, is the combination of model-based and model-free approaches. So what that means is basically you can construct your model on the fly. Yeah. And so on the right, you could see the illustration for that. So basically what we were doing with value iteration and planning methods is we took the value, we did the learning. Sorry, not like that actually. So you had a value iteration when you just by using the model, we did the planning step. So we were iterating to get the optimal function, and then we were acting on it. So only the upper parts were used. Now in the reinforcement learning, so in learning methods, what you did instead is you had the value, you did some acting, you get an experience, and from the experience, you learn directly the best action. Now, what you could also do is you don't know the model, but you act, you get experience, and you are not just using the directly learning here to get the value function, to update it, but rather you also learn the model of the environment. Yeah. And once you have that model, you could also use the planning methods to get a better value, action state value or action value function estimates. Yeah. And from that, you can learn a better policy. So you can combine this in different ways to use both experience and a model, which you get from my experience, to get a better estimate and then to get a better action. And that's also the approach which in some ways followed by this famous AI agent. So the AlphaGo, for instance, does some decision time planning. It means that from a state, it doesn't just use the experience, but rather it also looks ahead with value iteration based on a model which it learned by, well, getting the experience. What else? So what else do we have? So of course, it's we did not get rid of dimensionality curves. Yeah, so you still have the Q table is a table. Yeah, so once you get more states or more actions, the table just grows tremendously large, and it's very easy to run into memory problems. So you just don't have memory to learn it on your PC to store a table. Yeah. So you have to store the number of states times number of action values, which is a lot. And one way to do that is to solve this problem is to use approximation. So there is a lot of ways how do you, well, actually the Q table is already an approximate or it's an estimate. And then you could use also some functions to approximate it. But the common approach, which is very popular now, is to use deep Q learning and to approximate basically the Q table with a neural network. So I think there is great work by DeepMind people who actually introduced the working deep Q learning mechanism, and there are a few tricks you have to follow there, and it's a little bit a heuristic to make it work. So it's a trial and error, but it's been shown to get really great results. So I'm not going to go into detail on that, but you could also find a talk on YouTube from the guys doing it. So then taking it to the next step. So what we assumed so far is that we have a Markov decision process, so that the state only depends, the next state only depends on the current state. Yeah, and the truth is that in reality there are a lot of problems which cannot be accurately modeled by a Markovian process, and in that case you would need to have this temporal component brought in. So you have to consider the states before and the history of them. And one way to do it is also has been shown to get some great results, at least in some games and so on. That's the most popular benchmark. So Atari games. So the deep learning with recurrent neural networks, where you use a recurrent neural network to approximate not the Q table, but the action value table. So this already brings me to the summary of the talk. So what have we been talking about for the past hour? Basically, what I have introduced to you is a brief tutorial or brief introduction to stochastic optimization, which is a toolbox for solving a lot of different optimization problems. And the key point here is really that you want to get this delayed rewards, so rewards which might happen in the future. So you don't just look at this state, but you actually consider the future in some way. I have introduced to you the formal definitions of stochastic optimization, so in particular the Markov decision process. Then we went over through the planning methods. So how can you actually compute the optimal policy for your problem when the number of states and actions is small? Yeah? So this is the scalability issue of planning methods. And when the environment model is available. So when you know the model and your number of states is manageable, you can just compute the policy in advance. And this is nowadays not really the most popular way of doing things, because everybody wants to do learning and so on, and neural networks. But actually, this is quite an effective way for many, many problems. So do not disregard it if you have it, if you happen to have a problem which suits. And then we went on to the basics of learning methods. So in particular, I've shown you an example of Q-learning. This is what you do if a model of an environment is not available to you. And if you have larger problems, we have really a lot of states, then I suggest you take a look at deep learning and maybe use deep learning for these problems. Okay, so that's actually it. And I just want to give you a few, so this is a brief tutorial, so I did not give you all the theory and I didn't give you all the praxis, but I gave you a sort of an outlook of what kind of problems you can solve and what kind of methods you could use. And so for the theory, I really recommend you this, actually 3 books. So the Reinforcement Learning from Sutton, which is a great, let's say, lightweight book, which is easy to read and understand, and it introduces you a lot of methods. And then if you really want to go into theory and see if you can have some formal proofs for your problem and so on, then I suggest to look in Bert Seker's work, so in the dynamic programming and optimal control. Now, the examples I've used here were from my papers with colleagues from TU Munich. So if you want to know more, just find it easily. They're all available. And if you want to try out some reinforcement learning methods and so on, there is actually a great tool. I think it's also from DeepMind people, but I'm not sure. Is this OpenAI Gym? So it's just a Python toolbox, easy to install, easy to use, where you could try out different algorithms for yourself. Well, that's it. Yeah, waiting for questions.
Okay, thank you, Mikhail. Thank you for such interesting presentation. And I have questions for you. And first of all, do you try to estimate number of states in your models, or it just depends from number of sensors or something like this? How you can try?
Well, that depends on the problem. So in many problems, it's quite clear what is the number of states and what are the states, but it's a bit of an art to actually get a useful state representation, because as I said, there are problems where you do not have well observed state, and then you just need to figure out what's the best thing you can assume as a state. Yeah? And usually the larger is the state, so the more parameters you have in the state, the better. But then again, you run into scalability issues.
Okay, yeah, I understand that the less number of states is not good, yeah, but we can't do infinite number of states, yeah, and we just limited this number.
No, you cannot do infinite number of states. That's correct. So I mean, again, so if you use value iteration and if you have a well-defined problem, then you don't have to worry about it, because your your state space is well-defined and you have to go through all of it. Mm-hmm. Now, if it is infinite, or if it is continuous, or if you do not have a fully observable Markov process, then you cannot go through all the states no matter what you do. And in that case, you have to apply some kind of heuristics to actually find the best representation of your problem. Yeah. So as I've shown here, for instance, just have to go back a bit. So as I've shown here, as the different curves represent different number of states we actually consider. And the more you consider, the better. This is always the case. Yeah. So if you have a well-defined problem, but then also your computation will take longer, yeah? Or at some moment it will take that long that you cannot handle it anymore, and that's maybe where you have to stop. And you can of course apply some kind of binary search or whatever to find the best performing number of states, which still is acceptable.
How you can model your environment, and what does mean environment? You can see the interact with environment. Your models, or it is a real case, maybe some.
Well, it can be a model, it can be a real case, it can be a model of real case. So all three is possible. So basically, the environment is your process or your state, yeah. And whatever you chose as your state representation. So for a scheduling problem, this is a well-defined problem, sort of, because your environment is really the sensor and the state of the sensors and of every sensor, yeah. And then interacting with environment means you schedule this sensor and you see what happens, yeah. And then you schedule another one and you see what happens, and then you find the best one. Yeah. So now, if you are talking about some robot, I don't know, so the Roomba, which is trying to find the best way around your apartment to vacuum it, then, well, you have to define somehow your states and rewards. So what do you want a robot to be rewarded for? To get the most dust, to cover the most surface, and then the state, respectively, some coordinates or something like that. Yeah? So if you have a real world problem, or like autonomous driving or whatever, then you probably have to spend some time to figure out what state represents your problem best. And what reward do you want to get? Yeah, so you have to, it's for rewards, it's very often, for instance, for games, this is very often heuristics. For instance, if you consider some games, some like Atari games, where you have to go through a level, I don't know, or a Mario game, you have to go through a level and then collect some points on the way, but also you have to complete the game and not lose the game. And this is a bit tricky to define the reward here, because the best reward you get for completing the level, but then also you might want to get some rewards on the way for points you collect. And how do you choose it? How do you define the reward? You might define a negative reward, for instance, if you lose a level in a game. So that's so if you don't have a well-defined problem, then or if you don't have a, let's say, easily defined problem as scheduling, then you might want to experiment a little bit with different representations.
Thank you. And just one question about your formula on the slide. What does mean R? It is a reward, yeah, for update your Q table here.
Correct.
R.
So the R is the sampled reward. So that's the reward you get. So it's not a reward, it's the reward you observed. Yeah. So you do it at every step.
Okay, thank you. And we have some questions from the chat. What kind of type of task we can't solve using Markovian network or Markovian decision process? What kind of task, for example, just for example?
Well,
and another question:
yeah.
which kind of task we can solve, we can be solved by Markovian network here, just for example.
So, well,
maybe
strictly speaking, you can solve probably everything with it. The question is how good you can solve it. And the reason for it is that, well, in real life, almost no processes are Markovian. So I don't know, consider like financial markets. It's very hard to define a state which is Markovian, because it always depends on the history of states. It depends what people did in the past. So people buying stocks, they also consider what money they have and what they bought in the past and so on. So it's always in the decision somehow. So, and then there are problems like scheduling, yeah, so which can be well defined as an MDP, because you do not consider the history, yeah. And the thing is that you could approximate many processes by Markovian processes, because you could simply just say, okay, I don't care what happened in the past, yeah, and then you just learn the best. Yeah. But then, strictly speaking, it's not going to be an optimal value, but it's going to be an approximation of it. So I would say, maybe as an example, maybe the financial markets would be the process which you cannot use Markovian MDP for which you cannot use MDP, whereas maybe some robotics and control problems which have a much more well-defined state, they can be used as MDP. The other thing is that, for instance, like the Atari games, yeah. So this example, I think it's been shown that many games cannot be modeled properly. So how the agents are playing games usually is they observe a picture, pixel by pixel, they feed this into the network as a state. So your state is the current picture. And if you're playing an Atari game, for instance, if you're playing the game where you have to like shoot this ball, I don't remember the name, you have to shoot the ball to the upwards to hit some moving targets. So the targets are moving, yeah. So no matter what you do, this is not Markovian. As looking at a single picture, you cannot really figure out everything. So there are ways to go around this. You can, of course, say, okay, then to approximate it with Markovian process, I'm not taking only one picture, but I'm feeding 3 pictures into the agent. And this is your state. And from 3 pictures, one after another, you can already maybe devise some mechanism so to estimate where is it moving and so on. So then it gets closer to Markovian, yeah, but it's still not, because actually it also matters where you were before. So because the agent is moving below, yeah, to shoot the ball. So basically it's no way you put it unless you consider the whole episode is not Markovian. So it's been shown to be approximated well with MDPs, but it's been shown even better to work with recurrent neural networks. So by considering the time.
Okay, thank you, Mikhail. And I guess the last question, may you tell us about your further studies? Will you use deep learning in your studies or not, and etc.
Yes, actually, I did. It's not, there's no published work at the moment, but I actually used to do in my final months in TU Munich. I used to also work with deep learning, and specifically the problem was, if I go off to it, the problem was really with dimensionality. So I have also had some works applying. So random access problem, actually, if you complicate it enough, so if you can make this problem really interesting, and then at some moment you run into problems with computation, and then you have to use deep learning, and it works quite well. Actually, it's really popular to use it now. So in communication engineering, deep Q learning, it's a fancy keywords.
One moment, I guess that we have one question. If we can't describe the finite number of states, it means that Markovian don't fit for this, yeah, for this task. If we don't.
Well, strictly speaking, if you do not have a finite MDP, then there are a lot of theoretical properties which do not hold. Yeah, so the value iteration, the policy iteration, the Q-learning, nothing is really guaranteed to give you a result. So the theoretical properties are changing. And what was the second part of the question? Sorry.
So it means that if we can't describe the finite number of states, we can't use Markovian network for this task.
No, that's still, I mean, as a sense, so you can use whatever you want for whatever task you want. The question is how good it's going to work. So in that case, also, if you have an infinite MDP, you could still approximate it with a finite MDP by using the state aggregation, by using discretization, or by using state augmentation. The question is really how well is it going to work? Yeah, and this depends a lot on the problem. Yeah, so if you have like in that case, yeah, let's say random access. So actually what I didn't explain is that the access probability is a continuous variable. So it's between 0 and 1. And you can actually choose any of them. And of course, the more you discretize, the closer you get to the optimal solution. And the more coarse you discretize, the worse is the optimal solution. Yeah? But the thing is that it's just a variable between 0 and 1. And it gives you already an infinite MDP. But it still works really well. Yeah, so you approximating by finite, by just discretizing one value is very easy, and it gets you a tractable solution. As I've shown here, this is So this the upper parts, so the best case scenarios, we were not limited by the infinite nature, and we were because we discretized, and still works really well. Yeah. So it really depends a lot on the problem.
Okay, thank you, Mikhail, and I guess that we doesn't have any question. So thank you so much. Thank you for your presentation.
Thank you for inviting me.
It was very interesting so much, and we will glad to see you in the next year in our school. Okay.
Yeah, all right.
maybe you will tell us about deep
Yeah, let's see
learning.
about it.
Yeah. Okay.
Maybe.
Thank you so much.
Thanks. So what now? Do I just switch off?